I want you to do something for me right now. Just look at your hand.
Mm.
Or if you're driving, just tighten your grip on the wheel. Feel the structure of it, the bone, the blood.
Right.
We're conditioned to see biology, right?
Right.
We see skin, cells, tissues, standard issue earthly materials.
But if you zoom in, and I mean way in, past the biology, past the chemistry, right down to the atoms, you find something that, frankly, doesn't belong here.
It doesn't belong on Earth because Earth didn't make it. And that, for me, was the hook that grabbed me the hardest when we started looking into this. It's the concept of star stuff.
Yeah.
The iron that makes your blood red. It wasn't made in the Earth's crust. The calcium in your teeth. The nitrogen in your DNA. They're immigrants.
They're cosmic refugees.
Exactly. They were forged in the fusion reactors of ancient dying stars.
It really forces a shift in perspective, doesn't it? You stop seeing yourself as just a biological thing and start realizing you are quite literally a nuclear byproduct.
So, welcome to the deep dive. Today, we aren't just doing a biology lesson. We're tracing the biography of those atoms. We're synthesizing insights from, the heavy hitters, Carl Sagan, Stephen Hawking, Neil deGrasse Tyson, to track the entire life cycle of a massive star.
From birth through its life.
Right. The delicate balancing act, the iron crisis, and then finally the most violent event in the universe, the supernova.
And violent is really the key word. We look up at the night sky and it seems so peaceful, static almost.
Right, romantic.
But the sources are so clear on this. To get the ingredients for life, you need catastrophe. You need an explosion so bright it can outshine an entire galaxy.
Billions of stars.
All at once.
It's cinematic stuff. So let's unpack this. How does a star even work? I think the common assumption, and I was guilty of this, is that it's just a big ball of burning gas.
It's like a bonfire. Yeah.
It burns till the wood's gone, and then it just fades out.
That's the intuitive view, but it misses the dynamic tension that keeps a star alive. Stephen Hawking in his work uses this brilliant analogy, a balloon.
Okay, a balloon. Walk me through that. How does that map onto a star?
Okay, so think of the star as an inflated balloon. You have two forces in this constant tug of war.
Right.
On the inside, you've got the air pushing out. In a star, that's the incredible heat and pressure from nuclear fusion. The core is just smashing hydrogen atoms into helium, releasing enormous amounts of energy.
And that pushes outward.
Pushes outward, trying to expand the star.
And then rubber of the balloon.
That's gravity. A star is so massive, its own gravity is just relentlessly trying to crush it down into a single point.
And so you got this deadlock, fusion pushes out, gravity pulls in.
And as long as they cancel each other out, the star is stable, it shines, it supports its own weight.
But this leads to a weird paradox, the sources point out. You'd think a really massive star one with way more fuel than our sun
should live longer.
Yeah, it's got a bigger gas tank. It should just run for longer.
You would think so. But here's the irony. The more massive the star, the stronger its gravity is, the tighter that rubber squeezes.
Okay.
So to keep the balloon from collapsing, the core has to burn its fuel much, much hotter.
Just to fight back.
Just to generate enough outward pressure to fight that gravity.
So it's the ultimate gas guzzler.
Exactly. Our sun is like a Prius. It sips its fuel, runs for billions of years. But these massive stars, the ones that become supernovae, they're Ferraris with a brick on the accelerator.
They live fast and die young.
They burn through all that fuel in just a few million years.
And when they start running out of fuel, that's when things get really complicated. This isn't just, tank is empty, car stops.
Not at all.
This is what I started calling the fusion ladder. It felt like a thriller movie where the walls are just closing in.
It is a race against time. Because stars are resourceful. When the hydrogen runs out, gravity starts to win. The core contracts.
Okay.
But that contraction, it raises the pressure and temperature even higher.
Which unlocks the next level.
Precisely. It gets hot enough to fuse the ash of the last cycle. It starts fusing helium into carbon. The star stabilizes again.
It buys itself a stay of execution.
For a while. But then the carbon runs out. Core shrinks again. Gets hotter again. Now it's fusing carbon into neon, then oxygen, silicon, sulfur.
It's literally building the periodic table in its core.
Climbing up the ladder of elements 2 protons at a time, it's stellar alchemy.
But all the sources emphasize there's a hard limit, a dead end.
And its name is iron.
The villain of the story. Why iron? Why is that the breaking point? Why can't it just fuse iron into something heavier and keep going?
It all comes down to nuclear binding energy. Neil deGrasse Tyson explains this so well. For all the lighter elements, hydrogen, helium, carbon, when you smash them together, they release energy.
You get a net gain.
A net gain. That energy is what keeps the balloon inflated. It pays the rent against gravity.
It's an exothermic reaction. Pays out more than you put in.
Correct. But iron is different. It's the most stable element. It has the least total energy per nuclear particle. And that means fusing iron doesn't release energy.
It costs energy.
It absorbs it.
Oh, wow. So suddenly the engine stops generating power and starts sucking it.
Exactly. The star's been running on this energy for millions of years. But the moment the core turns to iron, the transaction flips. The batteries die.
Instantly.
The check bounces.
There is zero outward pressure. And gravity, which has been waiting patiently this whole time.
Finally wins.
And it wins in a fraction of a second.
Yeah.
That is the iron crisis.
The speed of this is what's so hard to wrap your head around. This isn't a slow deflation.
No. We are talking about the core of so something bigger than our entire planet.
Yeah.
Collapsing to the size of a city. In milliseconds.
And the outer layers.
They're no longer being held up, so they just rush inward.
Oh.
At about 70,000 kilometers a second.
That's terrifying. 70,000.
Roughly a quarter of the speed of light. And they're rushing toward a center that has become unbelievably dense.
Okay.
The collapse is so violent that electrons and protons in the core are literally smashed together to form neutrons. The core becomes what Sagan calls a single giant atomic nucleus.
A brick wall of neutrons.
The densest thing imaginable.
Yeah.
And those outer layers that we're falling in, they hit it.
They hit that wall and they bounce. That's the rebound. That is the supernova. The shock wave just blasts outward, tearing the rest of the star to shreds.
And the brightness is
staggering. For a few weeks, that single explosion can outshine every other star in its galaxy.
combined.
A billion suns.
A billion suns all at once.
And this isn't just theory. I mean, we have historical records of people seeing this happen with the naked eye.
Oh, absolutely.
Yeah.
The most famous one is the guest star of 1054 AD.
Right.
Chinese astronomers recorded a star that just appeared on the 4th of July, funnily enough.
And it was bright.
So bright, it was visible in broad daylight for weeks. You could walk outside at noon, look up, and see this thing shining.
And I love that connection to the American Southwest, the Anasazi people.
Right, in Chaco Canyon, there's rock art, a painting on a cliff overhang. It shows a crescent moon and a bright star right next to it.
And they've matched it up.
Astronomers calculated the position of the moon on that date in 1054, and it's a perfect match. They were documenting the exact same explosion. It's amazing. People on opposite sides of the planet looking up, seeing the same cosmic violence. And today, if we point a telescope at that spot,
We see the Crab Nebula. It's the shredded guts of that star, still expanding outward 1,000 years later. It's a cosmic crime scene photo.
So I want to clarify something because you hear these terms used interchangeably. Nova and supernova, they sound similar.
But they are very, very different events. Sagan makes the distinction really clear. A nova is like a skin condition. A supernova is heart failure.
Okay.
A nova usually happens in a binary system, 2 stars. One is a white dwarf, and it's basically stealing gas from its partner.
And it flares up.
Exactly. When it steals enough, the surface ignites in a fusion explosion. It's violent, but the star is still there afterwards. It can happen over and over.
But a supernova.
That's the end. The core collapses. The star destroys itself. One and done.
And the consequences for any nearby planets are drastic.
Vaporized is the word. You know, when our sun dies, it'll swell up into a red giant and probably swallow Earth. Sagan calls that grim.
It's just grim. Yeah.
But a planet near a supernova gets blasted with enough radiation to strip its atmosphere and boil its oceans in seconds.
So note to self, do not buy real estate near a blue supergiant.
Good call. Though the sources do offer a little comfort, advanced life is pretty unlikely to exist around supernova candidates anyway.
Because they live such short lives.
A few million years. Evolution just doesn't have time to do its thing. If you're smart enough to understand what a supernova is, your star probably isn't one.
That is strangely reassuring. Okay, so the explosion happens. The outer layers are blown off. What's left behind? That core that crunched down into neutrons.
Right, this is where we get the remnants, the corpse of the star. For a star that's massive, but not too massive, what's left is a neutron star.
The single giant atomic nucleus.
Exactly. I want you to imagine a sphere about the size of Manhattan.
Okay, time.
About 10 or 12 miles across. But inside that tiny sphere, you have the mass of a sun and a half.
The density numbers here are just... That's where my brain starts to break. Sagan has this bit about a teaspoon of the material.
A single teaspoon of neutron star matter would weigh about 1 billion tons. roughly the weight of Mount Everest.
In a teaspoon.
In a teaspoon. Hawking has this great thought experiment. He says if you could somehow drop a lump of it on Earth, it wouldn't just sit there.
No.
It's so dense, it would just punch a hole straight through the pavement, through the crust, the mantle.
Like a stone dropping through air?
Exactly. It would fall right through the center of the Earth, shoot out the other side, stop, and fall back down again.
It would just keep going.
Oscillating back and forth, turning the planet into Swiss cheese until friction finally let it settle at the core.
That is a horrifying image. A teaspoon that assassinates a planet. And these things are spinning, too.
Right.
Wildly fast. It's the conservation of angular momentum. Like an ice skater pulling their arms in.
To spin faster.
Right. When that huge star collapses down to 10 miles across, it spins up. The pulsar in the Crab Nebula, the one the Anasazi saw, spins 30 times a second.
A city-sized object spinning 30 times a second. And because of its magnetic fields, it shoots out these beams of radio waves and light, like a lighthouse.
Kick, dick, dick.
And that's why we call them pulsars. They're cosmic metronomes.
Okay, so that's a neutron star, fate number 1. But there's another door, a darker one. What if the star is really, really massive?
If the remaining core is more than about, say, 3 to 5 times the mass of our sun, then even the neutrons can't hold up the weight.
The gravity's just too strong.
It's too strong. The collapse doesn't stop. It just keeps going.
The balloon vanishes.
It collapses to 0 size and infinite density. A singularity. It becomes a black hole.
And gravity gets so intense that the escape velocity exceeds the speed of light.
Exactly. There's a boundary, the event horizon, and once you cross it, nothing gets out. Not even light. Not even information. It's a one-way trip.
And it's funny, these were debated for so long. Stephen Hawking actually had a famous bet with Kip Thorne about Cygnus X1.
He did. Hawking bet against it being a black hole.
Which seems so weird. He's the black hole guy.
It does, but he called it his insurance policy. He figured if black holes didn't exist, he'd have wasted years of research.
But at least he'd win the bet.
He was hedging his happiness.
And the prize was?
A subscription to Penthouse magazine.
Laughs. You can't make that up. The greatest minds of our generation betting smut on the fabric of space-time.
Science is a human endeavor. He did eventually concede the bet, by the way. Cygnus X1 is, in fact, a black hole.
So we have these two fates, neutron star or black hole. But I want to circle back to the star stuff idea. Because the explosion itself, it isn't just a spectacle, it's a factory. And this is where it connects back to us.
This is maybe the most crucial takeaway. Remember the iron crisis? How the star fuses elements up to iron and then just stops.
Right. The fusion ladder ends at iron.
So where do we get gold, platinum,
Yeah.
uranium? Those are all heavier than iron.
The star couldn't make them while it was alive?
The energy dynamics just don't work. To fuse iron into gold requires a massive input of energy, more than a normal star can provide.
So where does it come from?
The only place in the universe with enough sheer, raw energy to force those atoms together is in the supernova explosion itself. It happens in the shockwave, in seconds.
So the gold in a wedding ring.
Was forged in the violent death of a star. It was created in a flash and then blasted out into the galaxy.
That gives a whole new meaning to precious metals. You're literally wearing the debris of a cosmic catastrophe.
And it's not just the jewelry. Sagan calls it scattering the chemically enriched guts of the star. If the star didn't explode, all those elements, carbon, oxygen, silicon, they just stay locked in the corpse. Useless.
The explosion is the delivery system.
It creates the rare stuff and it distributes the common stuff. It seeds the gas clouds that eventually collapse to form new stars and new planets.
Which brings us to our sun.
Our sun is a second or third generation star. It contains the recycled ashes of earlier supernovae. That's why we have rocky planets. That's why we have carbon for life.
We're living in a graveyard that's been repurposed into a nursery.
That's a perfect way to put it.
But the connection to life goes even deeper than just the ingredients. This is the one insight from Sagan that really blew my mind. The link between stellar death and evolution itself.
It's a fascinating theory. A supernova blasts out cosmic rays, high-energy particles moving near the speed of light.
Right.
These rays travel for millions of years, they cross the galaxy, and they strike Earth. And they don't just bounce off.
Some of them get through.
They get through. They can strike living cells, they can strike DNA, and when they do, they can scramble the code, they cause mutations.
And while we usually think of mutation as a bad thing,
Evolution relies on it. Natural selection needs variation to work on. Without random mutations, life is just static. Sagan suggests that maybe key leaps in biological history, the Cambrian explosion, a shift that led to primates, could have been triggered by a spike in cosmic rays from a nearby supernova.
That is.
Yeah.
That's wild. A star explodes 1,000 light years away, and 1 million years later, a gene mutates on Earth that eventually leads to us walking upright.
We are solar-powered, built of star stuff, and our biological destiny might be partially driven by the deaths of distant suns.
It just dissolves the barrier between us and space.
Mhm.
It's not out there, it's woven into us.
It is. We're part of a cosmic fugue. Stars are born, they live, they die in these spectacular explosions, and their ashes form the next generation.
And the next generation includes us.
It does.
So if we step back, what's the big takeaway? For me, it's that the universe isn't a static backdrop. It's a violent, creative, churning engine.
And that the violence is necessary. That's the thing to remember. Without the Iron Crisis, without the collapse and the explosion, the universe would be so boring.
Just hydrogen and helium.
Just hydrogen and helium floating around. No Earth, no life, no gold, no blood. The violence creates the complexity.
I want to leave the listener with one last image that stuck with me. We talk about the neutron star, that teaspoon that weighs a mountain. But the sources point out that this power isn't just out there in deep space. The neutron star teaches us about the hidden power of the commonplace, because the nucleus of every single atom in your teacup, in your own body, is held together by those same forces.
The awesome power of the neutron star is lurking in the nucleus of every atom you touch. We are balancing on the edge of these incredible forces every moment of our lives.
We are, quite literally, walking atomic energy. Thanks for diving deep with us today.
Always a pleasure.